All right, so here's the project, PMA 123, and this is down in the optional section that uses the Flare VM, because not everybody's going to have a good enough system to run these Flare virtual machines, but if you do, I highly recommend it. And so we're going to analyze this file called Hello4, and as usual I'm going to shove this to the side so I can just bring up my live Flare VM and make it good and big. All right, that should be pretty good. All right, so let me move my instructions over here so I can follow. All right, so I have this thing called Hello4, and you can run it to see what it does. So I put it in my downloads folder. So if I open this and change to downloads, whoops. All right, and do a dir, you'll see I have something here called hello4.exe. And if I run that, it says, hello, I use DLLs. This is just a hello world program. It doesn't ask a question or anything. It's just a very simple program that, in fact, the source code for that program is here. It's nothing but a library and one line of printf. So how complicated could that be? And the answer is very complicated to do this, which is about the simplest program you could possibly make. So let's take a look at that program in PE view. So if you got the Flare VM, everything is already installed. You just search for PE view, and you can open the file, and it is Hello4. All right, so you see the layout of this file. And so here you've got the usual stuff at the top, the MZ and the DOS header and the PE header. And what we want to look at is the import address table, which in this file is down here in the iData section. So this is the header for the iData section, and here is the actual iData section itself. This is what it looks like all in hex, which is not very handy. But if you expand this, it will show you the components. And here, for example, is the import address table. These are all the Windows API calls it makes. So it calls initialize, debugger present, terminate process, get last error. Page after page of this junk. And all of this stuff is from kernel32.dll. So it only uses one Windows library, and it uses what looks like 30 or 50 functions from that library, ending with raise exception. So what we can see how this is all laid out, and the point is you're going to have some challenges here where you have to fix programs that have broken import tables, and this will come up a lot in these optional projects. Fixing a code with programs with bad import tables is a fairly common thing you have to do. So these all come from kernel32. Now if you look at kernel32, here's raise exception, for example. There's a P file address and a data address, 5954C and 5D9DA. And I'd like you to understand how these addresses work. So if you look at this location, 5954C, the P file is the literal location in the binary structure of this file. So I can look for that address, 5954C, in the iData section. And see 5954C is here, 5954. This is 048C. So there is the 5954C over here, and it is 4 bytes, DA-D9-0500. This is a 32-bit address, 05D9DA, and that's what I saw here. So this address contains that data. That's what this is showing me. And that address is what points to the raise exception function. Now, you can look. Now we can see, let's see, I thought I have this. Yeah, all right, good. All right, so now we can look at the import hints and DIL names here. And here we see the names of all the API calls, and here's the name of the library, kernel32.dll, and before each one, there's a 2-byte hint, which has something to do with how it's found. And so we can find raise exception. Is what you want. Let me make this smaller so I can see it. Yeah, raise exception is what I want. So I go down here, and I think it's It's down at the bottom. Raise exception, and here's the 2 bytes before it. So this 2 bytes before it down to there is the stuff that matters, and this is 6 in. There, the 4004 is the 2 bytes before it, and this is now the ASCII spelling out raise exception, and then a null terminator. So that is the label. It's the name and the hint. Hint is the 2 bytes and then the name, and it also has DIL names. That's the name of the function it calls. Now, this, all right. Anyway, the point is you can calculate how these things relate. This is a relative virtual address. The P file points to the real location in the file, but the section loads at a different address. And the pointer to raw data, if I go to the section header for iData here, it shows me that the relative virtual address is here, 5D1000, but the pointer to the raw data is 594,000. So this is where the data for this section is stored in the executable file, but when it loads it into memory, it takes all the sections, and you see there's quite a few sections here, text, RData, data, iData, and so on. It takes the sections and sort of separates them and lays them up in memory sparsely with gaps between them. And you'll see it if you run it in, say, Ollie, which I think I'll just do right now to make it more clear. All right, so if I run this thing in good old Ollie, which, here we go, okay. Yes. Okay, so here's Ollie, and if I load this thing, which is Hello4, in Ollie, and then I view the memory, you'll see how it loaded into memory. And the point is, notice what's going on here. The text section is here. Now, every program generally starts at 400,000, and by the way, that's because I modified this to always start on 400,000, which we'll talk about later. But anyway, this is its preferred address. So it loads this section at 400,000, which is 1,000 big. Then it loads this one and this one. These always are ending in even thousands and always launching on even thousands, all these sections, and they're not that big. The actual amount of data here is often less. So the program is sort of exploded. It comes as a little like a book with the pages shut, and when it loads into memory, it spreads them apart and puts them in these more sparse locations here. That's why there's a difference when loaded in memory and when stored in the executable file. That's why you have to go and see where it's actually going to load. So this only has C100 raw data, but it's going to take at least 1,000 in memory once it's loaded. So the point is you can see the difference here for the iData section. The pointer to the raw data is 594,000, but the relative virtual address is 5D1000. So that is 9, A, B, C, D. That would be 4,000 minus 400. That is 3C100 in hexadecimal, the difference between those. So the actual address in memory is 3C100 higher than the P file address within the file. So that's what you can figure out. And if, all right, and you can see it in the memory map. Anyway, that's pretty much the heart of it here. The only other thing that's kind of fun is if I, let me download a fresh copy of this file, or I'll try removing it. There's this program you download called Set DIL Characteristics. And this, you see it right here, setdilcharacteristics.exe. And what I did was I told it to stop relocating this file. I'm going to turn it back on with the +D flag. +D for hello 4 will make it relocatable again. Now, I can't open it while this program is locking it, and I think probably this one too. So I close those programs. Okay, now it's made this program relocatable again. Now if I load it in Ollie, you're going to see the effect. Ollie. Okay. And now I load file Hello4, and then I view memory, and see now Hello4 is loaded up here at FD1000 instead of 400,000. Now you can see if you load it in PE view, if you load Hello4, you can see up here, let me find out where it is. It's in the image optional header. There, here. Here it shows you image base 400,000, which is true of all Windows executables I've ever seen. There may be upon some that don't have it, but this is where they generally are. So it wants to load at this address, 400,000. But all modern versions of Windows have address-based layout randomization. So every time they load it, they randomly move it in memory. So if you look at where it actually loaded, in your Ollie, it's not at 400,000, it's up at FD1000. And then these pieces come up, loaded up. So if you don't want it doing that, because you're trying to analyze the code and you don't need this headache of yet another offset, then you remove that flag with this program. And that's where I was at first. So I put in the -D, set DIL characteristics, and now it's not going to do that anymore. Now if I run it in Ollie, and I load Hello4 and view the memory, now it's right where it belongs at 400,000, 401, and so on. So it makes it a little easier to analyze the way it loads in memory. And anyway, in this project, you have some flags defined by just finding out where pieces of it are. And then you've got a program that uses 2 DLLs, and you have to find the other DLL. I don't tell you, you have to find out what DLLs are actually loaded by it. And then you've got one here where you have to find the address where it loads. One of the kernel32.dil, and then you have a broken file that has some kind of problem with the DLLs that are loading. You're going to have to figure out what the problem is and fix it so this program will run. So anyway, there's a few places where you get to practice with PEView and HXD, analyzing these files and then fixing a broken file at the binary level, which is all good stuff for you to learn how to do.